And
Yes.
let's
Hello.
see, we don't see the slides online yet, so
No, give me 1 second, please.
okay. Oh, you are
Now,
online. Okay.
can you see them?
Yeah, we're waiting for presentation mode, I think.
Okay, yeah,
Okay, it looks good.
perfect.
All right, so Kevin is going to be speaking to us about comparing failed to full outbursts.
Yes. So, hello everyone. I would like to first thank you all the organizers for organizing this amazing conference, both remotely and there in Cagliari. And today I'm going to talk to you about our latest paper that it's about what we call fail transition outbursts that are more known as fail outbursts. So as a very brief introduction, as all of you know, the X-ray emission from X-ray binaries can come from two main components that are a subthermal component that comes from the accretion disk, and it can be described by a multicolor disk black body, and a comptonized component that can be described by a power law and comes from the corona. Here in the left panel of the slide, I show two examples of energy spectrum, one dominated by the subthermal component of the accretion disk and another one dominated by the comptonized component. The contribution of these components to the X-ray emission varies during outburst, and depending on this contribution and the spectral and timing properties of the system during outburst, four spectral states are usually defined. The low Hart state, where the energy spectrum is dominated by the comptonized component, the high soft state, when the X-ray spectrum is dominated by the subthermal component, and in between we define normally two intermediate states, the HIMS and the SIMS. A very useful tool to study the evolution of the source along these states is the hardness intensity diagram, or HID, that you have seen several examples in the previous talks, where we plot the intensity in the y-axis versus the hardness ratio in the x-axis, where the hardness ratio is defined as the count rate as the ratio between the count rate of two different energy bands. At the beginning of an outburst, a system is located here in the bottom right side of the HID, and then evolves through the low Hart state following this gray line. At some point, the source makes a state transition through the intermediate states and reaches the high soft state in the top left side of the HID. At this moment, the evolution reverses at lower luminosities than before, and the source comes back to the low Hart state and finally reaches quiescence, where no X-ray emission is detected. This shape in the HID is known as the Q track due to the shape that has. In the past, we thought that this evolution was common in all black hole systems during outbursts. However, nowadays we know that this is not true. Here in the left panel, I show the long-term light curve of GX39 obtained with RXT PCA, and we can identify two types of outbursts: those marked with blue arrows and those marked with red arrows. In the right side, I show the two representative HID of both types of outbursts. The blue one representing the outburst marked with blue arrows, and the red one related to those with red arrows. In sometimes black hole systems evolve through all the spectral states and show the evolution that I described before. This evolution corresponds to the outbursts marked with blue arrows that show the Q track in the HID, and since they show the full spectral evolution, we call them full outbursts. However, other times black hole systems do not reach the high soft state during outbursts, and they either remain in the low Hart state during the whole outburst or make a small transition to intermediate states to come back later to a low Hart state without reaching the high soft state. These outbursts are known in the literature as fail outbursts or Hart state only outbursts, among other names. However, we think that all these names do not represent exactly these events. Because of that, we propose the denomination fail transition outburst, or FT outburst for simplicity. Coming back to the case of GX39, FT outbursts are those marked with red arrows, and you can see that that in the HID, they remain in the right branch of the HID that corresponds to the low Haar state. What do we know about FT outbursts? First, from previous studies, we know that they are fainter than full outbursts. We know also that they are shorter in duration than full outbursts. And as I said, we know that there are two types of FT outbursts. Those remaining in the low Haar state that follow the blue track that I show here in this HID, or those making a small transition that follow the red track that I show here in the HID. So knowing this, we ask this question at the beginning of the project. Can we predict whether an outburst is going to be a full or an FT outburst from the beginning? That's it, from the very first days of the outburst? In order to answer this question, we did the following. First, we carried out a systematic search of FT and full outbursts in the literature. Then we built a sample of 56 black hole systems undergoing 128 outbursts. And we compared all the available X-ray data of FT and full outbursts. At this point, we realized that we only had enough data of sources showing both full and FT outbursts in 3 sources, GS39, H1743, and GRS1738. And finally, we studied the optical and infrared data of outbursts of GX39, -4. So the first question we answered was, are FT outbursts usual? From our sample, we found that 36% of the sources show FT outbursts, and that 33% of the outbursts included in our sample were considered FT outbursts. This suggests that phase transition outbursts are more common than we thought in the past. And these results is in accordance to previous results, for example, the one in Tetarenko et al. In 2016, that pointed out the same. The next thing we did was to study the relation between the X-ray peak intensity and the time spent in quiescence between outbursts. If we assume that the X-ray peak intensity that a source reaches during outbursts depends on the accumulated matter in the acquisition disk during quiescence, the longer a source remains in quiescence, the brighter the next X-ray outburst would be. So here in this plot, I show in the y-axis the X-ray peak intensity obtained with PCA, and in the x-axis I show the time spent in quiescence between outbursts that we got from Tetarenko et al. In 2016. In blue, I show data from full outbursts, and in red from phase transition outbursts that you have here, the sources that we consider. And we found that the time spent in quiescence between outbursts of full and FT outbursts is very similar, as you can see. The main difference between them is the peak intensity that we already knew that they were different. Full outbursts are brighter than FT outbursts. So this suggests that we cannot predict whether an outburst will be a failed one or a full one, only taking into account the time that has spent in quiescence before this outburst. The next thing we did was to compare the rise of the outbursts in the X-ray light curves and HIDs. Here, I only show the representative case of GX39. In the left panel, we can see the light curves. In red, again, phase transition outbursts, and in blue, full outbursts. And the same in the HID. And we found that during the first days, the X-ray light curves and HID of both FT outbursts and full outbursts overlap during the first 20-30 days, except some exceptions. And we found the same for other sources, A1743 and GRS1738, and using data from SwiftBat and Maxi. So what conclusions we have so far? We found that the longer time in quiescence does not mean brighter outbursts, and that X-ray light curves and HIDs of full and FT outbursts overlap during the first days. This suggests that both types of outbursts are driven by the same physical mechanisms, and that maybe, or according to the current models, the only difference between FT outbursts and full outbursts is that black hole systems during FT outbursts do not reach the mass accretion rate needed to make a straight transition.
Okay, 2 minutes, Kevin.
Okay, I will go very fast. So we did the same with optical and infrared data from smarts of GX39. Here in the left panel, I show the optical and infrared light curves in different bands, and we found that we cannot distinguish between them. Is it true that they don't overlap as in X-rays, but if I remove the colors from the plots, it's not possible to say which is which. We also studied the color magnitude diagrams of FT and full outbursts, and we found that they lay in the same region of the color magnitude diagrams. And finally, the most promising result, thanks to the smart coverage of the GX39, we could also study the light curves before the onset of the outburst. Here in the top panel, I show the long-term light curve of X-ray light curve of GX39, PCA, and SwiftBat. And in the bottom panel, I show the optical long-term light curve with smarts. And in blue, I point the intervals before the onset of full outburst, and in red, the intervals before the onset of FT outburst. And we can see that GX39 appears to be brighter before FT outbursts. So how can we interpret that? Depends on where the optical and infrared emission comes from. If we assume that the emission comes from mostly from the disk, that could mean that the outer parts of the disk are more massive before FT outbursts, and that's why they are brighter. If the emission, on the other hand, comes from the jet or the corona, that means that the properties of the jet of the corona are different before FT outbursts and before full outbursts. And although we cannot answer the question that we asked at the beginning of the talk totally, we open a lot of lines of research that we can follow in the future. And I think I can finish with that. Thank you very much.
Thank you very much. So do we have any questions in the room? If not, then I'm going to quickly jump to Greg.
Okay.
Hi, Kevin. Thanks for the talk. So you mentioned one of the possibilities would be different radio properties. Have you guys considered looking at the history of GX59-4's radio X-ray correlation and seeing if there's a difference?
Very briefly, yes, the problem is that we did, however, we found that we didn't have enough data at the beginning of the outburst to compare them. Most of the radio data was at very advanced stages of the outburst.
And are there any questions now in the room? Sorry, we can't hear if you're speaking.
Question, no question.
Oh, no question. Okay, now here. Okay, Jonathan?
Yeah, thank you. Very nice talk. I was wondering, did you look for if there is any correlation between the duration of the soft state as a function of the time passed in quiescence?
No, we haven't checked that. Actually, it's a good point that we could.
Okay, thank you.
And again, checking in, I'm still not seeing questions. The room, no. I have a quick question, actually. You mentioned the infrared might have different interpretations of what's driving this. I know that, I can't remember if Dave Russell and others had done these analyses on GX59, right? But they were looking at excess infrared to try to see if the infrared at a given time was due to disk versus jet. So when you look at the infrared, I guess it's a sort of excess you might be assuming would be driving this or responsible or related. Can you say something already about that analysis, whether you can conclude where it's coming from?
No, I'm afraid not. Actually, I'm not sure if Dave Russell has already done this, but we have plans to work in that direction in the future.
Okay, well, if there's no other questions at this time, and of course, people can always put things into the Slack channel for Kevin, I'd like to thank him again. And